Okay, we're back from our exercise. Let's go ahead and discuss. So, in that exercise, what we did is we used the data that we collected from our sample of farmers, right? We used our sample data to find what we would call descriptive statistics. Just information about our data. We calculated the mean, it's a measure of the center of the data. We calculated the variance, that measures the dispersion, but it does so in a way that's kind of funny, and it gives us huge and unwieldy numbers, okay? And then we calculated the standard deviation, which is a much more usable measure of the dispersion of the data. Okay? So let's unpack that and think about that a little bit more together. First, remember, you are calculating the sample estimates of the mean, variance, and standard deviation. Alright? Those are, as I said, they're estimates of the population. Estimates, by that I mean they are attempts for us to predict, or they're an estimated guess as to what the true population descriptive statistics are. Okay? But they're not perfect because you don't have all the data. Now in our case, we have all the population data, so we can actually compare it. So let's do that. The population mean is 900. The population variance is 156,000. And the population standard deviation is around 394. All right? That's the information for our population. All right? Now we look at that variance and like, man, that variance is huge. This doesn't communicate any information to me before, like I was saying before. You tell me that the average income is 900, let's say 900 a month, okay? It's 900, and then that's the variance. That doesn't help me. It's huge, it's ridiculous. But this helps me a lot. This helps me to understand how dispersed the data is. There's a standard deviation of 394. 394, let's say, gonocetes. That means about 68% of our population lies between 900 minus this and 900 plus that. Okay, that gives us an idea of how well distributed the data is. All right. But now, what you calculated, the sample mean, sample variance, and sample standard deviation, they're all estimates of these population values. In a certain sense, we could say, these are the true values. These are the real ones. These are the ones that we really want to know. These are estimates of those. Well, let's just get an understanding of what we have here. All right, we've got 4 students. So let's learn what each of yours are. Okay, I'm just going to ask you to read them. And at first I thought I would have you report the variance, but let's not take the time. Those numbers are too big and they're not very comprehensible anyways. So let's just go around the room and then you tell me what your mean and standard deviations are.
At 975 and 670.
Okay, yeah, let's round it off. 1,000? 259? Oh. Was it? 293, okay.
625.
625.
430.
430.
413. 1
431.
No, the one in front of the 3.
Oh, 413.
Yeah.
Got it. And I remember that. Okay.
1156.
Okay.
404.
404. Okay. So these are a bunch of sample data, sample estimates. It's a sample estimate of the mean, sample estimates of the standard deviation. None of them are quite right. They're all, I guess, decently close. There's some variation in them. Now when we look at this, and this is, I'm getting a little bit ahead of myself, I'm going to come back to it in a minute. When we look at this, one thing that we will see is that these estimates of the mean, these sample means, the sample mean is itself a variable. Does that make any sense? each one of you represents a different sample from the population. Right? Each one of you represents a different sample. This would be as if we sent 4 research teams all to take random samples of farmer data from northern Ghana. Okay? There's 4 random samples from the data. Alright? Each one of those random draws gives us a data point about the sample mean. That means the sample mean is itself a random variable. It's a random variable that estimates the random variable of the true population mean. Does that make any sense, or is that too convoluted? No? Does that make sense? Okay. What we would find, and I'm going to get to this later, but I'm just going to do it now for this one. What we would find is that if we kept doing this, let's say that we did this all day long. All day long we were taking random samples, calculating sample means. Take a random sample, calculate sample means. Take a random sample, calculate a sample mean. We would generate a lot of sample mean data, right? What you would find is that the average of this data, the mean of your sample mean, would be equal to 900. If we took enough. Now, do you want to see if that worked? We might not have enough data, but will you calculate the mean for me? What's the mean of our sample mean? And we only had 4 observations. That's a little bit small. 937.5. Can someone give me a confirmation?
937.5.
937.5. Now guys, that's so close. 937.5. That's how close that sample mean is to the true population mean. And that's with only 4 samplings. Alright, does that make sense? Is that interesting to you? If we sample, if we collect data enough, we will eventually have the true population. Okay? Alright, we're gonna come back to that in a minute. That's really important. That's what we're just doing there. Okay. Alright, so let's keep going. Alright. Now, we are still in the topic of measuring some variation, so we're going to do the next one now. The next one is going to be the coefficient of variation. A coefficient of variation, what this does is provides us a measure of variation that doesn't depend on the unit. So we just said that we had the standard deviation. The standard deviation is measured in the same units as the mean. So it's really helpful. I illustrated why it's helpful, right? It's like 10,000 Ghana cities is the average, 1,000 Ghana cities is the mean. That really helps you to understand the data. But the standard deviation is in the same units. It's in Ghana cities. We might want to have a measure of variation that is unitless. There's no unit. And the reason that might be helpful is it allows us to compare 2 different random variables and to say which one of those 2 random variables has more variation than the other. The coefficient of variation allows us to do that. The coefficient of variation is the standard deviation of data divided by the mean of the data times 100. So in our example of the farmers, the mean was 10,000 Ghana cedis. The standard deviation was 1,000 Ghana cedis. So if we took 1,000 and we divided it by 10,000, first we would notice that the units, the Ghana cedis, they cancel out. So now there's no units anymore. And then we have 1,000 divided by 10,000. That would be 0.1. Multiplied by 100 times 10. Coefficient of variation is 10. Did I do that right? I think so. Let's trust me. And then when people watch the video later, they can tell me if I did it wrong. Okay. That would be the coefficient of variation. There's no units. Now, if I wanted to compare that, let's say I took a sample. So I did my sample in Ghana. Now I'm going to do a sample in Tanzania. Same number of people, smallholder farmers. okay? And I get a coefficient of variation of 20. That means that there's more variation in that data set from Tanzania than there is in Ghana. There's more variation. Without calculating this, I wouldn't have been able to tell you. So the coefficient of variation allows us to compare across different samples. So here's an example here that makes it a little bit more interesting. Let's say that I was studying prices and I wanted to compare gold prices with corn prices or maize prices. The average gold price is 1,593 whenever this was made. The average corn price is 750. Okay. The standard deviation for gold is 85, and the standard deviation for corn is $1.25. Which one is more variable? Which one has more variation in it? Gold prices or corn prices? Gold? Taking it, yeah. Maybe gold? Anyone else want to take a guess? Maybe it's corn. You think it's corn?
The gold.
Is it gold? Do you think it's gold? The nice thing about this example is that when you look at that, you actually have no idea. It's really hard. It's really hard to tell which one varies more. Gold has a higher standard of deviation, for sure, but it also has a much higher mean.
Yeah.
Corn has a much lower standard deviation, but a much lower mean. So when we look at that, I can't tell. So we can calculate the coefficient of variation by using the formula that we had on the slide before. Standard deviation, so for gold, standard deviation divided by the mean times 100. 85 divided by 1,593 times 100. Okay, that's our gold coefficient of variation. And then our corn coefficient of variation, 1.25 divided by 7.5 times 100. Okay. 5.3% variation in gold, 17.3% variation in corn. Corn is much more variable. It's much more volatile prices than gold in this example. That might be important. That might be interesting to us. But it's really hard to see if you don't use the coefficient of variation. Okay, let's go to the next exercise.